Exercise 11.10 is asking you to draw the mechanism for a few radical halogenations. So these are going to be radical mechanism. I'll draw what they're asking for in this first one. I'll draw the molecules so that you can sort of see the overall change that's happening. And then we'll talk about how these mechanisms work step by step, and we'll draw them out. So they're asking you to do chlorination of methylene chloride. Now, methylene chloride is dichloromethane. So one carbon, meth, all single bonds, ane, and dichloro, that means you have two chlorines on your molecule. The other two bonds will be to hydrogens. So that is methylene chloride. And they want to chlorinate that, and they're going to use a radical mechanism. So you'll use molecular chlorine in the presence of light, this H nu. H is Planck's constant, so it's just a constant. This V-looking thing is actually the Greek letter nu, and it means the frequency. That is symbolic of the energy of light. If you remember from General Chemistry 1, the energy of light is equal to Planck's constant times the frequency of how frequently the light waves hit you. And so that's just representative of light, the H nu. So if you have chlorine gas that you shine usually ultraviolet light on, it'll add a chlorine onto this original molecule, so that you would have your original molecule with the two original chlorines. But you'll add a third one, and the other hydrogen will still be there. And as a side product, the hydrogen that you replaced will bond to the second chlorine here. You would have HCl. But the main thing, the story of the carbon molecule, is that you add a chlorine onto that. So how does that happen? One step at a time. Radical mechanisms have sort of three stages. They have, like any story, they have a beginning, a middle, and an end. Now each of these are going to have jargon, fancy jargon terms in radical mechanisms. The beginning is called the initiation step. You form radicals in that step. The middle is going to be called the propagation step. That's where one radical gets stabilized by making another radical. So you propagate the radical. And then the end is called the termination step. So we're going to have these three steps in all of the mechanisms in exercise 11.10. So while we discuss this, just to emphasize that point, I'm going to put that general outline beneath each of these exercises, so that when we get to them, we sort of have that framework to work with. Okay. So, let's think about these one at a time. How do you make radicals in the initiation step? Let me actually make a little room. So how do you make radicals in the initiation step? The initiation step for radical halogenation happens when the light hits the halogen molecule. So chlorine is diatomic. It always exists when it's in the elemental form, chlorine all by itself. It always exists two chlorine atoms bonded to each other, like so. And in this bond, in real molecules, the bond between the chlorines is vibrating at room temperature at around 10 trillion times per second. And so like a spring, there's a certain tension in that bond as it vibrates. Now, imagine a kid playing with that spring, pulling it apart and pushing it so that it goes fast and fast and fast. That's what happens when you shine light onto this molecule. Light, this wave of electricity that travels through space, that pushes this spring, it pulls it apart and makes it vibrate even faster. In fact, it vibrates so fast that the bond breaks. The spring snaps. Now, when this breaks, which atom will those electrons prefer to go onto? Chlorine on the left or the chlorine on the right? Well, they're both equally electronegative. And so the electrons prefer them equally. So one electron in the bond goes onto the chlorine on the right, and the other electron in the bond goes onto the chlorine on the left. Notice that when this happens, we're going to create two radicals. This, by the way, is called homolytic cleavage. It's a term worth knowing. The cleavage is you're cleaving the bond, you're breaking the bond. And that's just stated again in the suffix lytic. Remember, the suffix lysis or lytic means to break apart. If something is analytic, you're breaking it down. Ozonolysis is using ozone to break apart pi bonds and sigma bonds. This is homolytic because it breaks apart in the same way for the atom on the left and for the atom on the right. The electrons are going equally in both directions, the same in both directions. The prefix homo means same. So it's breaking apart in the same way for both atoms, and it's really breaking apart. So homolytic cleavage. Well, we end up with that step, but we end up after that step. And here we're doing this with chlorine, but it would work just the same with bromine, is we end up with two radicals, two chlorine radicals. And you could see the unpaired electrons on those two chlorines. Those unpaired electrons are really reactive. They're going to snatch off, claw away any atom that they first knock into. So they're really reactive, and that opens up potential. That means you can get a lot of things done with them. That's exciting. But it also means that they're dangerous. So if you ever work with radicals, make sure you're extremely, extremely careful. Okay. So much for the initiation step. The initiation step creates radicals. The propagation step takes the radicals that you made and reacts them with an otherwise stable molecule. Now, in this molecule, what they're giving us was methylene chloride, which we said was dichloromethane, if you give the IUPAC name. And so, and let me just switch the chlorine and the hydrogen here. It doesn't really matter which one they're on, I just want the hydrogen to face the chlorine. And they're three-dimensional molecules, so you can twist them and rotate them however. So what ends up happening here is that in this step, in the propagation step, a radical that you have gets stabilized, and in the process, a new radical forms. So this is going to steal one of these hydrogens. Just like in the previous exercises, you see that these radicals often rip a hydrogen off of a molecule because they react with the first thing they run into, and all of these carbon chains bristle with hydrogens on their surface. Hydrogens always face the outside world, so the radicals most often run into them. Now you're going to form a new bond between these. And whenever you form a new bond with radicals, you use fishhook arrows and you point them at the space where you're forming the new bond. One electron in the bond will come from the chlorine, the other one has to come from the hydrogen. So the hydrogen only has electrons in this bond here. One of them is going to get pulled toward this really, really sticky radical on the chlorine to create the new bond. There are two electrons here, though, and we've only described what happens to one of them. The other one goes back onto the carbon. So we can use a fishhook arrow to show the creation of that radical. And so, in that step, we make, with these two curved arrows, we make HCl. Well, we have the chlorine bonded to the hydrogen, so HCl. And then we're going to have a radical on the rest of this molecule. So we have sort of the same thing, but a radical on the carbon, an unpaired electron on the carbon. Now there are other side reactions that can happen here. And so if you were to look at for example, the mechanism that's given for this in the textbook, you will see other side reactions. For my class, it's important to me that you know the linear progression, the main steps that carry these molecules on the left to these molecules on the right. The side reactions are not of essential significance to me. And so here, this is all you would have to show for this propagation step. So in the propagation step, one radical gets stabilized, but in the process, a new radical forms. The formation of that new radical gives us its name, propagation. Now, once you have this carbon radical, the carbon radical can react with the other chlorine atom, the other chlorine radical that we formed in the beginning. So when two radicals come together, they form a bond to each other and they destroy the presence of radicals. So they terminate the radical reaction. So we're going to form a new bond between the two radicals. Whenever you form a new bond with radicals, you use curved arrows, the fishhook arrows, and they point to the space between the radicals where you're forming the bond. So we'll have this curved fishhook arrow pointing to the space between these atoms, curved fishhook arrow pointing to the space between those atoms. And the single barb at the end of those arrows is telling us that we're just moving one electron. And in that termination step, what you end up with is the product that you had to explain. So all three chlorines and the hydrogen, that's what we had to explain up here. You can see along the way we also produced the HCl, but that's not the focus here. The focus is the story of this carbon chain. This molecule, by the way, is called chloroform. In general, if you have 3 halogens and 1 hydrogen on a single carbon, that's called a haloform. If the 3 halogens are chlorine, then it's chloroform. If there are 3 bromines, it's bromoform. If you have 3 iodines, it's iodoform. Chloroform is used in sort of like cartoon villains. We'll put this over somebody's mouth and they'll fall asleep. It's chloroform. Okay, so this was the first radical mechanism that we've learned in this chapter. And you can see it has this beginning, middle, and end. The initiation, where you get homolytic cleavage to create 2 radicals. The propagation, where one radical gets stabilized, but in the process another radical forms. And then a termination step, the end of the story, where 2 radicals come together to neutralize each other. Okay, so let's go through that same process just to build confidence, make sure you see the pattern, the forest and not the trees, by drawing the same type of mechanism, radical halogenation, for the chlorination of chloroform to produce carbon tetrachloride. Well, we know what chloroform is. Let's just draw this out. Chloroform is what we made in the last reaction. We have 3 chlorines and 1 hydrogen on a methane molecule. And when you chlorinate it, you take molecular chlorine in the presence of light, that's what the H nu is standing for, and you end up making carbon tetrachloride, so that's adding another chlorine onto the molecule. Notice the effect of these radical reactions. They add a halogen onto a carbon chain. It's very powerful because the halogens allow you to do, they act as leaving groups, so they allow you to do substitution reactions and elimination reactions. Having a halogen on the molecule is a window to the world. It opens up all the reactions you know to you. So let's think about initiation. Now for these radical mechanisms, just think about what halogen you're using. Here it's chlorination. If it said bromination, you just have BRs instead of CLs. But the mechanism would be the same. You would take the molecular halogen, so the 2 chlorines in this case, and when you shine light on them, you get homolytic cleavage. 1 electron in this bond goes onto 1 chlorine, the other electron in the bond goes onto the other chlorine, and you end up with 2 radicals. So you have these 2 chlorines, and they each have an unpaired electron, so they're each radicals. So that's the beginning. How about the middle, propagation? In the propagation step, we take one of these radicals, it's going to be stabilized, but in the process we're going to make a new radical. The new radical that we'll make will be made out of this carbon chain that they're asking us to react with the chlorine. Now, actually, I'm going to replace this with the other one, just so the hydrogen and the chlorine are facing each other. So the radical is going to steal a hydrogen, or if you want to be really fancy, you could say it will abstract a hydrogen. It'll steal a hydrogen off of the carbon chain. And so you're going to form a new bond between this chlorine radical and the hydrogen in the propagation step. Anytime you form a new bond in a radical reaction, you use a fishhook arrow, and the fishhook arrow points to the space where the new bond is forming. The chlorine radical will contribute its one unpaired electron to form that bond, but it will need another electron to form a bond. And so it will take it from the bond that the hydrogen is in. The hydrogen and one of its electrons will get ripped away from the molecule it's in and will connect with this very reactive chlorine radical to form that new bond. Now, in that step, we show what happens to one of the electrons in the bond between the carbon and the hydrogen. One electron, represented by the fishhook arrow, goes to form the bond, but there are two electrons in that bond. So what happens to the other one? The other electron in the bond moves onto the carbon, and so we have one fishhook arrow that shows the creation of that new radical. So when that reaction progresses, we have hydrogen bonded to chlorine. That's one of our products. And the other product will be the rest of this molecule, but the carbon now will be a radical. Okay, so that's the middle of the story. Now, the end. This radical, this carbon radical, will pair up with the second chlorine radical that we formed. And the two radicals will stabilize each other. They'll each donate one unpaired, very reactive electron. They'll pair up, and then you won't have radicals anymore. So the radical reaction will terminate. The carbon radical will donate its one electron. We use a curved fishhook arrow to point to the space where the new bond is forming. The chlorine radical also contributes one electron, the unpaired electron of the radical, to the space where the bond is forming. And in the process, you end up making a new bond between the carbon and the chlorine. So we created this new bond. And so this is the mechanism for the radical chlorination of chloroform to produce tetrachloromethane. So we have the beginning, the initiation, where we form the radicals using homolytic cleavage. Then we have the middle, the propagation, where one radical is stabilized, but in the process, another radical is formed. And then we have the termination step, the end of the story, where two radicals come together to create a bond, a stable bond. Okay, let's really drive that mechanism home by walking through it just one more time with two different molecules. Now I'm going to go through this a little faster because we've already explained this in detail 2 times. So they want to know what happens if you take ethane, and here I will draw ethane. I'll draw it out. Eth prefix means you have 2 carbons. An means you have all single bonds. E means it's a hydrocarbon, ethane. And you want to react it with do a chlorination, a radical chlorine reaction. So you have molecular chlorine with H nu. Now again, in these 3 mechanisms we're using chlorine, but on a test or in life, you actually more often use bromine. Bromine adds more selectively onto molecules. It's more careful about where it adds onto the molecule than chlorine is. And so bromine really tends to be the halogen that you do this with more often. So you should be able to draw this same mechanism with a bromine instead of a chlorine. It's the same thing, just anywhere we have Cl, replace that with a Br. Okay, but here this question is asking for chlorination. So it's asking to do chlorination to produce ethyl chloride. That's really the same thing as ethane, just one of the hydrogens is replaced by a chlorine. So one of the hydrogens replaced by a chlorine. Well, we're going to have a beginning, a middle, and an end. The beginning, the initiation step for these radical halogenations is always the same. You just take the halogen, when you shine ultraviolet light on it, UV light on it, it makes this bond, which is already vibrating around 10 trillion times per second, 10 to the 13th times per second. It makes it vibrate faster and faster and faster until the spring snaps. One electron snaps back onto one chlorine, the other electron snaps back onto the other. So you get this homolytic cleavage of the chlorine molecule to create two chlorine radicals. Okay, so that's the initiation step, homolytic cleavage to create two radicals. After you have those radicals, those really reactive molecules, you can do a propagation step to make them react with an otherwise really unreactive molecule. I mean, if you notice that here you have an alkane. Alkanes are very stable. They don't have any partial charges. They don't have any electronegativity. So you can't find, and they don't have any extra electrons. If you look here, you squint as hard as you can, you won't find any nucleophiles or electrophiles on this molecule. So there are very few reactions you can do with alkanes. In fact, there are really just two that we'll learn in organic chemistry 1 and 2. That's you can burn them, light them on fire, and turn into carbon dioxide. Not particularly useful all the time. Well, I shouldn't say that. At the same time, that's what powered all of the light for most of human history, and also we still use in gasoline, etc. But for synthesis, it's not very useful. And the other reaction is this halogenation. So in halogenation, in the propagation step, we would take one of the radicals we made, and it will steal or abstract one of these hydrogens. So the radical will be stabilized, but in the process, we will create a new radical. Now this is going to bond to one of these hydrogens. Whenever you use a radical to create a bond, use a fishhook arrow not to point it at an atom, but at the space where the bond is forming. So this chlorine radical will contribute its one unpaired electron to form that bond, but you need another electron to form the bond. The other electron is going to come from the hydrogen that this is ripping off the molecule. So the hydrogen has these two electrons associated with it. One of them gets stolen and gets contributed to the new bond that you're forming. So these two fishhook arrows are going to represent the creation of a bond between the hydrogen and the chlorine. At the same time, the bond that is breaking between the carbon and the hydrogen has two electrons in it, and we are only showing what happens to one of them. The other one, we would use a curved arrow to show, snaps back onto the carbon of ethane. And so we propagate the radical. We create a new radical. And it's formed on that carbon. So now we have a really reactive carbon, carbon radical, excuse me. So that's the propagation step. A radical gets stabilized, but in the process, a new radical is formed. Then the termination step, we can take the other radical that we made in the initiation step, and we can combine it with the new radical we formed in the propagation step. So both of these can contribute one unpaired electron. This is the opposite of homolytic cleavage. It's called coupling. This chlorine radical can contribute its one electron to the bond. The carbon radical contribute its other electron to the bond. Notice I have two fishhook arrows, and they're not pointing at atoms. They're pointing at the space where the bond is forming. In this coupling reaction, this termination step, we end up making chloromethane. So we have the same molecule, just instead of the radical, we have a chlorine attached. So you'll notice that was the molecule that we wanted to explain the formation of. And the overall effect was to put a chlorine onto a hydrocarbon. In this case, put the chlorine onto an alkane, which is really profound because you turn a molecule that's not reactive at all, an alkane, into an alkyl halide, which we know is really reactive. This chlorine can now act as a leaving group. You could do substitution reactions or elimination reactions. When you do elimination reactions, you create pi bonds, and when you create pi bonds, addition reactions are open up to you. So having that halogen leaving group on your carbon chain, putting it there through this radical halogenation, is very powerful because it opens up the whole window of the world to synthesis to you. Substitution, elimination, and through elimination, addition can be done once you have a halogen on a molecule. So in this video, we've walked through a linear progression to describe how a halogenation the radical mechanism of a halogenation works. Like I said, if you look in the book, there will be side reactions that occur. For example, in the propagation step or in the termination step. But what I want you to be able to show are not the side reactions, but the essential linear reactions that cause this transformation in a radical mechanism of an alkane. And that's what we've walked through for 3 separate reactions in this video.